Okay, thank you very much. It's great to be here with you today. So I'm going to talk about building large-scale protocols from MPC, from different building blocks, like linear secret sharing and FHE and garbled circuits. Sorry about this, but it's going to have to, to work. So for a little bit of context, let's go back to the 90s when the internet was first created. It was mostly public because the browsers were very limited in the amount of logic that they could run. This changed with the second version of the web, the current version, and now browsers can implement complex privacy-preserving mechanisms. And as a result from that, we have confidentiality, which is a cornerstone to the growth of Web 2. Without the ability to hide information from one user's, from the private eyes of other users, it wouldn't be possible to build the web as we know it today. The problem with Web 2 is that it's actually centralized, so there's a lot of trust that you need to place on the service providers. And that's the problem that Web 3 comes to solve. But in doing so, we have kind of abandoned this confidentiality element, which was key to the growth of Web 2, because most of blockchain technology is actually public. So that generates a huge space of opportunity at the intersection between confidentiality and decentralization, which is actually a space that can be filled in by privacy-enhancing technologies, and in particular by MPC. The reason for MPC to be prominent here is because it's natively decentralized. So it talks about a distributed network, and all of the nodes in that network play the same role, hence you have decentralization. And actually we have seen today a lot of talks about MPC protocols already in this space, occupying this space. Most of them have been around signatures and ECDSA. So this presentation is going to be a little bit a zoom out from that situation, and is going to look at trying to push the boundaries of MPC and trying to build a large-scale general purpose compute protocol based on MPC. Other privacy-enhancing technologies like zero-knowledge proof and FHE and TEs are not ideal in this case because they don't have this key decentralization component. Of course, you can add it later, but MPC is privileged for that reason. Just a quick note on notation. By decentralization, these are quite loaded terms. So by decentralization, I mean the distribution of control and decision-making. And by trust minimization, by trust, what I mean is the degree of trust you need to place on other players in the network, which is usually is removed by cryptography, but not completely, like we've heard also earlier today. This is an interesting framework for thinking about and understanding decentralization. It basically tells us to think about it in terms of three different axes, which are orthogonal. One is the architectural aspect of it, the other one is the political, and the other one is the logical. By architectural, what I mean, or what Vitalik means, is essentially the number of physical nodes that you have, and also the type of protocol that you're using to minimize trust. By political, the key question here is how many institutions or organizations do you have actually behind those nodes? And this is a very important question for MPC. You know, the worst case scenario for MPC is actually that there's only one entity behind all of your nodes, because this is like the worst instantiation of a civil attack. And the base case scenario is the opposite, where one node means one entity. So that's a very important question, and it's related to the onboarding process of those nodes. And then we have this other dimension, which is the logical one, which doesn't exist in blockchain. This here, the question is essentially, can you slice the network in two separate or more than two sub-networks and still provide the services that they were intended to? With a blockchain, it's not possible, because the service that a blockchain provides is that of maintaining a global consistent state. And if you slice the network in two, you're forking the network, and you have two states that will drift apart. But with MPC, we will see that depending on how you build the network, if you work with clusters, those clusters might have a certain degree of logical decentralization. So this framework gives us a perfect way of structuring our challenges. So the logical challenges will be mostly around those clusters. The political challenges will be around two major attacks that I want to be talking about today. One is this civil attack I've mentioned, and the other one, we could call it the silent leakage of shares. And the architectural challenges are about what happens when we go big, both in terms of the size of the network, but also in terms of the size of the circuit that we want to run on the network. So there are three main building blocks to building an MPC network: linear secret sharing, fully homomorphic encryption, and garbled circuits. And each one has advantages and disadvantages. I'm going to be talking about them in more detail, but just to give some starters, let's mention their Achilles heels. So the problem with linear secret sharing based approaches is that they're very intensive in terms of round complexity and communication complexity. The garbled circuit solution is intensive in communication complexity, so in terms of bandwidth, and computational complexity is the problem of FHE-based solutions. So what I'm going to be doing is I'm going to introduce those primitives, those basic building blocks, but at the same time, I'm going to be doing that while contextualizing the challenges that I've mentioned before. So I'm going to be talking in parallel about those three dimensions: the architectural, the political, and the logical dimension. So beginning with LSSS, essentially, one thing you could do to keep things simple is, okay, I just have one network, and I'm going to think about Shamir secret sharing, for example. This network has 10 nodes, and what I'm going to do is distribute my shares across those 10 nodes. And then there's many more customers coming into the network, and one problem you may have is that of scaling up, because those nodes may run out of resources. That can be solved by virtualizing the nodes, so that now one node is actually not a physical machine, it's a virtual network comprising several nodes controlled by the same entity, but which can scale in terms of storage, compute, and bandwidth in a more eloquent way. So that's one problem that is interesting, but it's not that important. The most important problem here is what happens if you succeed in your network and people want to join in, so the network has to grow, or maybe shrink because some nodes are leaving. The right way of doing this, once you've already shared secrets, is to use proactive secret sharing, which kind of reshuffle the sharing and can do that so that now there's more nodes or fewer nodes in the shuffle. But the problem is that it's a very expensive operation. So you could die of success if you're all the time adding new nodes and every time you have to do proactive secret sharing. Perhaps a better approach is to cluster the network and to enforce one simple rule, which is that the clusters have to have a constant size. This way, if new nodes come to the network, all you do is grow in the number of clusters, but you don't need to touch the existing clusters. You still will have the same problem of nodes leaving one cluster, so clusters shrinking in size, and then you can, of course, run proactive secret sharing, but you can tackle that also from the token economic perspective. So you can create incentives for nodes to be good levers and give you enough time in advance to run that proactive secret sharing. But in creating clusters, of course, we have created a problem, which is the cluster management problem. So for you to have an idea of what I mean by this, it's essentially about synchronizing the different actions that the nodes in a cluster and that the clusters take. Because the problem is that you may have race conditions. Like imagine inside of a cluster, a node may see one request coming from customer A before the request from customer B and do some actions based on that. But a different node in that same cluster may see things around. So the request from customer B comes before. So we need a notion of a global clock. And you could do this with a sequencer, but it's a centralized solution. A better solution would be to use MPC for that. Why not? But even a better one would be perhaps to use a blockchain, because that is what they were designed to do, to get this global order of things on a ledger. So you can use that, and this way, all the nodes are going to have a clear idea of what event comes before which other event, and they're going to be acting synchronously. Now, of course, this creates the problem of gas fees, and also the blockchain could potentially become a bottleneck. But if you choose an L2, this might alleviate the problems so that it becomes a feasible alternative. Moving on to political challenges. We have, the typical taxonomy for security, static, adaptive, mobile, passive, and so on. I'm going to be talking about passive adversaries mostly, on the trust minimization side of things. But on the decentralization first, that's the Sybil attack I was talking about before. So the problem is that you may have one entity running more than one node. You can tackle this again from the token economics. So you can impose staking from the beginning. You can maybe run KYB and KYC as an additional measure, or some other stringent requirement for the onboarding. But the good thing is that as you grow as a network, the Sybil attack becomes more expensive. So you can relax those stringent onboarding requirements and tend and progress towards a more permissionless environment. Now, on the trust minimization side, we have also a very serious problem, which is that you're running your network, you think that things are going fine because you're not detecting any active attack on your protocol. But silently, behind your back, the nodes are actually sharing or exchanging their shares up to the point where they can reconstruct the secrets. This is a very tough problem because there's no way to detect this situation. This communication is literally going offline, completely outside of your protocol. So you can again play with token economics. You can create incentives for nodes to report each other. You can work with the architecture, and we'll see this solution a little bit later. And one interesting thing that you can do is encryption. You can encrypt the shares so that the nodes don't see the shares in plain text. They're always in encrypted form. This is what we have done, and we have called this eNMC, is one of our technologies. And so I'm going to give you a brief overview of how it works. Essentially, the idea is to use a different mechanism for hiding information. Instead of using secret sharing directly on the secret, what you use is you use encryption. We call it a particle, and it's actually a form of symmetric encryption. So you have this secret S that you multiply by a group element that is controlled by this blinding exponent that is what is going to get secret shared. So by imposing some structure on the field, you can manipulate the exponent with shares, which is very convenient, and therefore your sharing of the secret is actually a pair, is a two-tuple of the particle and a sharing of this blinding exponent. Now, one interesting thing is that particles are ITS, which means you can do them, with them whatever you want. You can publish them, put them on a blockchain, it doesn't matter, they're completely safe. They're also multiplicatively homomorphic, so you can perform as many multiplications on them as you want to, and you will still get a particle that hides the product of the plain texts. And the other interesting thing is that any operations you do with the exponents, they're all linear. And that's the reason why we can use encryption in a very lean manner. So let's imagine that we want to evaluate a sum of products. So we have S, which is the result, and it's a sum of any arbitrary number of terms, and each term is the result from multiplying any arbitrary number of factors. So one thing we can do is we particleize those secrets, we turn them into particles, and now we can multiply them directly because of the multiplicative homomorphism. And what we do next is we multiply that by a sharing of a blinding exponent, that is this rho sub k, that is computed in such a way that is equal to the sum of the blinding exponents of the particles that were used in the product, so that all the blinding exponents cancel each other out. So what you get is actually, after the sum, a sharing of the sum of product. Now, with this technique, before Jonathan Katz asked if we can get rid of the one round of communication, for example, for multiplying k to the -1 times x, if I understood the question correctly, I believe that with this technique, you can get rid of that round of communication. But going beyond that, what you can also do is add encryption on top of that, so that at no point any node is having access to the plain text of the shares during pre-processing and also during the online evaluation. So you can take a look at the formula in the middle. And notice that the sharing of this g to the rho sub k is actually being used in a linear fashion. So it's being multiplied by some public elements, and then it's being added. So you can replace it with an encryption. And so you can work with an encryption of that sharing that you would create in a pre-processing way without revealing the shares at any point. And then you, using the syntax of Pallier or Damgard and Jurek or from Castañez, you can compute the sharing of the encryption of the sharing of the result just like this. You can even go one step beyond this, and actually, by redefining rho sub k, you can now compute an encryption of a sharing of a particle hiding the sum of products. And the reason to do this is if you decrypt and reveal, what you get is a particle, which was the initial point, and so you can repeat the process over and over again. So very much like you do with LSSS, which you divide a circuit into layers, and the gates in each layer can be evaluated with no communication. Now you could do the same here, only that you're not dealing with simple gates, you're dealing with sums of products in an arbitrary way. So you're dealing with sort of super gates, and also with the addition that you can do the whole evaluation in encrypted form. So the shares are always in encrypted form. So to summarize ENMC, in essence, you have no secret shared multiplications. This means that multiplications are free. There is no penalty to multiplying a million things. It's the same cost as multiplying two. You can also work at the same time with a minimum number of shares. For example, in a passive setup, you can work with t plus 1 instead of 2t plus 1 because you're not locally multiplying the shares to initiate the BGW type of multiplication. And this leads to lower cost for the protocol. But in this context, the most interesting thing is the fact that you can work with shares of encryption, with encryption of shares all the time. So that you're never are lending yourself or exposing yourself to this attack of silent collusion behind your back. Because even if the nodes did collude, they would have to break encryption. Moving on to the architectural level challenges, remember this was about going big, both in terms of the circuit that you want to run, as well as in terms of the number of nodes that you want to be dealing with in the network. The best idea is to go for the two building blocks that remain, FHE and garbled circuits, because they minimize communication during the online phase, and this simplifies things a lot. For example, most protocols are proven in the synchronous framework that assumes that the delays are bounded, but this may not be the case if the network is really large. That wouldn't be a problem if you minimize communications in the online phase. So that's one reason why you would go for this. Another one is because minimizing communication means that you can now evaluate larger circuits. So let's talk about these two building blocks a little bit. Their syntax is the following. For garbled circuits, what you do is you garble a circuit, which is a kind of an encoded version of the circuit. Then you encode the inputs and evaluate that those encoded inputs, providing or obtaining encoded outputs. And what you do with FHE is you encrypt the inputs, then you perform the basic operations, addition, multiplications homomorphically, and then you decrypt the result. So if you do garbling with a network, or if you do key generation and decryption with a network, then you're building an MPC protocol using these cryptographic primitives. And that's when things get interesting. You can compare these two techniques, and there's a lot of details and nuances to that comparison, but at a high level, FHE-based MPC protocols have the advantage that they don't require pre-processing. And as a consequence of that, the communication complexity is completely independent of the size of the circuit. That's something very interesting to have in mind. Now, on the other side of things, garbled circuits are really fast when it comes to evaluating the circuit. Their runtimes are usually 1 to 2 orders of magnitude faster than FHE-based approaches. And also, it's cheaper to build active protection because essentially the evaluation is cheaper. The problem with FHE is that you're either facing a scenario where you want to repeat the same computation, so all the heavy machinery for FHE in several nodes, so you can then compare the results and protect yourself against active attacks. But again, that's very expensive. Or maybe you want to run it in one single node, but then you need a proof of execution in zero knowledge at the end, which again incurs in costs. I'm going to talk later a little bit about the efficient evaluation of leaky conditionals, which we think is an interesting thing to consider for garbled circuits, because it only applies to garbled circuits. And yes, as we said before, this attack of silently leaking shares or pieces of an encryption key is key also here. And so what we have now is another way to tackle it, this time from an architectural point of view. So you could think about dividing and conquering. You could think about two different types of nodes. One type is going to be a trusted node that you will assign to the tasks of pre-processing or garbling, or the generation of the keys and decryption in the case of FHE. And you know it. You know that you have to trust those nodes, so you put in place all the measures that you require for doing so, like all the onboarding requirements. You put them in place. If you need contracts with the parties, you get them sign those contracts. And also you enforce all the things you need for the protocol to operate smoothly, like, for example, having constant-sized clusters. But once you do that, then you have this other side of the network operating with completely different type of nodes that can be fully permissionless. So maybe you just require staking and that's it. Because those nodes, as long as the computational assumptions from the protocol hold, they won't be able to get to the secrets, because all they're doing is evaluating the circuit on encrypted or encoded inputs. So this way you get a much more dynamic network that can grow and shrink really without any constraint, and you have this flavor that we get from a blockchain. So you can at least get a portion of your network work like that, and this way kind of address the problem of silent leaking information when the nodes collude. Now, I'm going to be talking about conditionals first. Here the problem actually applies to any privacy-enhancing technology, and is really relevant because the minute you want to run large circuits, they're going to have a lot of conditionals and branches. And the problem with privacy-enhancing technologies is that if you want to evaluate a conditional, you kind of need to know a little bit about the information that you're trying to hide. So either you do a good job at hiding, and then you're not efficient at conditional evaluation, or vice versa. So you have these two scenarios. In option one, you are not leaking information, but then this means that the privacy-enhancing technology has to go through every possible branch in the program, and that might not be efficient because you have an exponential blow-up in the number of branches. So very quickly, as soon as you want to run a reasonable-sized program, you're going to hit this problem. Or if you're willing to leak some information, 1 bit per conditional, in some of the conditionals at least, you can then only evaluate those branches that you know are relevant to the result. So you're trading a little bit security or information leakage for performance in the online phase. It might be okay for some applications where the circuits are really big and there's no other options, or where people are fine with just leaking some information. This is actually an instance of a more general problem called declassification, which is a problem which you can build reactive MPC protocols, which means it's a type of protocol where the function you want to evaluate actually can depend on publicly revealed information in the middle of the computation. And the reason to use this technique is that it can simplify operations tremendously. I think we saw earlier today an ECDSA example which was making use of this technique. It was making public, I think it was phi times k as a public element, because it simplified the online evaluation. But you can use this in comparisons to simplify their evaluation, in fixed point operations, in the inverse, in the computation of inverse, in the computation of conditionals, as we saw before, or even the cut and choose technique. So it's a very efficient technique, and therefore it's a valid question to ask, whether you can support this with all the different building blocks. And the answer is yes, you can support it. For example, with FHE, you can always do a distributed decryption to declassify information at any given point in time. The only thing that you're paying for this is communication, because that operation requires communication. So you're kind of trading computational complexity for round complexity. But the interesting thing is that using this little trick, you can do declassification in garbled circuits for free. And this applies to Yao type of garbled circuit or BMR type of garbled circuit, where you kind of have this garbled table where you encode or encrypt the labels from the wires. So the nodes during garbling time, they identify those wires that they want to make public. And what they do is that they choose a label on purpose that leaks information about the value. For example, the label could end up in a 1 if the value is 1, or end up in a 0 if the value is 0. So this way, when you are the evaluator and you decrypt that entry from the garbled table, you will obtain a label that is telling you the value of the bit. And therefore, you can declassify information locally without incurring in any round of communication, without paying any price in terms of round complexity, which makes it a very interesting use of garbling, of circuit garbling. So to summarize and provide you some conclusions, we are dealing with a complex trade-off space, indeed. There's a lot of things to consider when deciding whether you want to go for one primitive, one building block, or another. Maybe a way to summarize this would be that if you want to work with linear secret sharing type of solutions, then you should be working with problems where the computation is very small. For example, signatures could be one example of that. Or maybe where information theoretic security is a requirement. Maybe it's some of, it's some legal requirement that you have. If you want to work with larger circuits, though, then it's probably better to work with FHE or garbled circuit type of MPC protocols. And here the rule of thumb would be, if you're really interested in minimizing the delay or the waiting time for users, which means you want to optimize the user experience, then you would be going for garbled circuits, because their online phase evaluation is orders of magnitude faster than that from FHE. Whereas with FHE, if you want to maximize the number of customers you want to serve with a given infrastructure, then that would be a good choice, because FHE doesn't require pre-processing, so it would make your infrastructure more efficient in those terms. So essentially, we've seen how we have structured the different challenges along those 3 dimensions. We have talked about logical challenges we have to do mostly with dealing with clusters. We have talked about political challenges, which have to do with the 2 main problems that we are facing. One is the Sybil attack. The other one is the silent leakage of shares. We have proposed one solution for the silent leakage of shares, which is encrypting the shares at all points in time. And then we have talked about what happens when we go big, really, and both in terms of the number of nodes and also in terms of the size of the circuits we want to run. And there we have considered using different primitives like FHE and garbled circuits. So one conclusion would be that we're talking about really a toolbox. There's not going to be a one solution fits all. This is more like a little bit like artificial intelligence, where you don't have one type of architectural for a neural network that really works with all type of problem, with text, with images, with sound, but rather you have one specific type of architecture for each one, for each type of problem. And with MPC is the same. So we don't know what the ChatGPT of MPC would look like. Maybe it's ECDSA, as it has been maybe suggested today. We don't know that, but for sure we're going to need different flavors in our toolbox to be able to address a generic range of use cases and problems. Thank you very much.